So this is part 2 of the Kubernetes multi-cluster networking patterns, projects, and guidelines series. My name is Sanjeev. So in the previous part of this series, we looked at the key architectural patterns, north, south, east, west, single network, multi-network, and several more. And then we went into detail on the north-south pattern, possible implementation choices, a little bit more detail on the DNS-based load balancing option. We looked at east-west multi-cluster, both in single network and multi-network mode. We also looked at the benefits of combining north, south, and east, west to get some of the benefits of both. So in today's call, we will now look in more detail at some of the open source community projects, primarily from CNCF project landscape. And we can see how we can categorize them into 4 architectural buckets that address the space. So let's do that. I'm going to jump ahead to where we left off. So what I felt was let's categorize these into 4 buckets. Okay. And the way I was looking at these categories was the first bucket is CNI plus projects, right? These are projects that started off as CNI drivers, CNI plugins, CNI being the Kubernetes Container Networking Interface API, but have since also extended beyond the basic CNI implementation into multi-cluster and other kinds of networking features. The second bucket are service meshes, right? These are upper layer application networking projects. The third bucket is implementations that are that implement the Kubernetes native multi-cluster networking API, a multi-cluster services API in particular. And then the fourth bucket is application networking frameworks that are largely or entirely in the user space and sort of target a different kind of an audience, some different operational model rather. So here's a bit of a busy chart, but hopefully a reasonable amount of information on different parameters and how these 4 buckets compare. There's actually a couple more that I couldn't manage to fit in, but hopefully this will give you some of an idea. So under the representative projects, right? CNI projects, CNI plus projects are like Cilium Cluster Mesh, and even Calico, I think, also calls their multi-cluster service as a cluster mesh. In the second bucket, you have projects like Istio, Linkerd, Kong. There's a few different ones there, Console and so on, Console Connect. There's the third bucket, which is Kubernetes native multi-cluster services API implementation. So projects like Submariner. And the fourth bucket is what we call sometimes virtual application networking. And a representative project there is Copper. So we can see that all of these 4 support sort of the single network basic model. Some of them also support the multi-network model. I don't think the cluster mesh projects do that currently. Feel free to correct me if if some of these projects have been updated and sort of have added some of these features now. This is my understanding. I have actually played hands-on with many of these projects over the last several months. So I think these are fairly accurate, but it's possible that some of these have been updated very recently. So feel free to please comment and if I'm missing something. The other dimension here, the feature here is whether the network policy in that framework is either identical to Kubernetes network policy, or is it very similar to a very similar extension of single network policy to multi-cluster. And here, none of these support the exact Kubernetes network policy API in multi-cluster mode, because Kubernetes network policy actually is a single cluster API. But these CNI plus projects, Cilium in particular, they do have Cilium network policy, which is quite like Kubernetes network policy, and it very seamlessly extends to multi-cluster mode. These other projects have their own OTCs, and to some degrees, they are loosely similar to Kubernetes network policy, in particular the HTOC, but they're not as seamless as in the Cilium case. Um, in terms of traffic management, the CNI Plus projects tend to focus on layer 3 and layer 4 features. And to some extent, they've added some layer 7 features. Some of these projects are even extending to add a complete service mesh in the future. So we'll see how that goes. The application service meshes um, do have extensive L7 traffic management and L4 traffic management. They have from the beginning been focused on um, application aware networking, which is essentially networking based on HTTP paths and uh, gRCP parameters and so on, right? Um, the Kubernetes native multi-cluster services API is an extension of single cluster Kubernetes service and is largely L3 network management. And the virtual networking projects like Scupper tend to be completely L7. So they're almost like name-based traffic routing and FQDN-based traffic management. In terms of how strongly these projects are aligned to an end-to-end zero trust networking architecture and a zero trust security architecture, I would say they all address it to some extent, but the service meshes and possibly the virtual application networking are most aligned with zero trust networking because of the kinds of, for example, whether these used traffic encryption right from the application pod to the application pod, as opposed to you being from cluster to cluster and so on, and the kinds of encryption they use. So I could spend a lot of time in going into each of these details. This particular talk is supposed to be a little bit broader, so we'll stick to that level for now. But there's a lot of there's a lot of background here in the reasoning for why I have categorized these in the following way. So just to kind of wrap up on the zero trust thing, for example, um, use of the appropriate infrastructure for certificate rotation, identity-based networking, cryptographic identities, um, the latest TLS ciphers, all those tend to be somewhat stronger in the service mesh and in the virtual application networking. But all of these projects are excellent. I mean, they have their pros and cons, and you should sort of look at what works for your particular use case. In terms of whether those frameworks are targeted for a somebody with you know admin privileges, um, the first three buckets do have an admin component, right? They are whereas the virtual application networking is targeted as being a framework that completely is under the control of the application developer or DevOps team, right? So these are entirely in user space. They do not require uh, cluster admins and Kubernetes admins to get involved at some or all parts of their day zero or day two operations. The first bucket is tied to, the multi-cluster networking architecture is tied to needing the same specific CNI at all clusters and at all locations. Whereas some of these other projects, they are actually at a slightly higher level. So they allow each cluster to have its own local CNI and then have a separate networking layer which sort of runs on top of the CNI layer. So this comes into play when you've got different clusters, some of which may already have different CNIs and so on. And in terms of non-Kubernetes endpoints, that is a work in progress in many of these projects. I don't believe that is true for the MCS API implementations, although in principle they could add that. So I think this is an area where there's still some amount of development ongoing. So this would sort of give you this, a way to look at these projects. Some of these have moved upwards from the CNI layer, and are accordingly more aligned with the L3, L4 networking. There's differences in the single network, multi-class, multi-network, the degree of zero trust implementation, the kinds of personas, and so on. Okay. Let's talk a little bit more about this service API and how that changes from going from single cluster to multi-cluster. So originally, and even now in Kubernetes, the service API resource is a single cluster resource, right? I mean, Kubernetes has these nascent projects like KubeFed and so on, which try to create a first-class notion of a multi-cluster configuration, but really they either have been deprecated or not caught on. So most of these resources in the Kubernetes API are actually single cluster resources. And you have to have a special effort to see whether some of those are implicitly can extend to multi-cluster or need new work, right? So the service API, the decision of the SIG multi-cluster was that one would need new API resources to have the multi-cluster analogs of the single cluster service. So in addition to service, you would also need objects like service export and service import, which then allow your single cluster service instances to selectively be exported by some clusters and imported by other clusters that need to access these services. And then you can do various kinds of filtering operations in terms of which kinds of clusters are allowed to export and import services and so on. So it's an opt-in model, right? By default, if you're creating a resource in Kubernetes, it is always single cluster. There's also, you will need to do things with concepts like cluster sets and cluster set IPs. So instead of the cluster IP, virtual IP front-ending an service, there will need to be a cluster set IP management and appropriate multi-cluster service discovery. So bottom line is that in the Kubernetes native world, it is not automagic that a single cluster service becomes a multi-cluster service, right? You have to do some of these explicit opt-in operations, and applications which have deployment manifests today will require some changes to move between single cluster and multi-cluster, and then need an implementation of that multi-cluster, either through an extension to the CNI or a separate controller, which then processes these new API resources. In contrast, some of the service meshes, and in particular, I'm talking about Istio here, I think this is true for many of the service meshes, they implicitly treat the Kubernetes service as a multi-cluster service across all clusters which are in the same service mesh control plane, subject to service namespace sameness. So if you have service foo in cluster 1 and namespace A, and service foo also in cluster 2, also in namespace A, and Istio mesh has data planes on both these clusters, the same mesh, it will automatically treat those two instances as subsets of the same multi-cluster service, right? So it is more seamless. You do not have to change your deployment manifests. You can opt out. You can actually use, again, this is implementation dependent, but you can opt out. But by default, it is somewhat more seamless between single cluster services and multi-cluster services. The Cilium cluster mesh takes a slightly in-between approach. It is also fairly seamless, but you do need to explicitly tag Kubernetes service objects with Cilium specific annotations to mark them as being global. And then you've also got a couple of filtering options for how you want to advertise or not advertise a particular service. So you can see that these different projects, they have to deal with sort of they have a lot of alignment with the Kubernetes APIs, but they also have some differences. And you have to be aware of that when you're, thinking about your automation. But also this is influencing how some of these APIs are evolving and how some of these projects both have their own native APIs and are adopting Kubernetes native APIs, like, for example, the Gateway API, which we'll talk about. And so you should be aware of these subtle details because they make a big difference. So here's an example where we talked about the Gateway API just now, right? And the Gateway API, you can map L7 route to a backend service. So if you were implementing this using the Istio implementation of the Gateway API, right? You could have a backend reference as a service, but that service could be both having backends in cluster A and cluster B, using the example we had earlier. And your HTTP route would actually get load balanced to endpoints both in cluster A and cluster B, assuming there's a networking path. So that's what we mean by sort of some of these subtle differences in the interpretation of what is a service and what is a multi-cluster service. So again, a bit of an eye chart, but let's think a little bit more about this, all these different APIs and how are they different and perhaps partly overlapping, and are they aligning or converging in the future? Let's start at the bottom with the Cilium APIs. So the Cilium APIs started off as implementing the Cilium project started off implementing the Kubernetes CNI API, right? Basic single cluster networking and so on, and services and service load balancing and the network policy APIs. And then they added Cilium CRDs to have more additional functions for networking and services in the single cluster mode. Then they added multi-cluster support through the cluster mesh extension, and that allowed them to, they decided to reuse the Kubernetes and the Cilium APIs. In fact, for the multi-cluster support, it requires the Cilium API, but you just have the annotation to mark it as multi-cluster. And then as Gateway API has been evolving recently, Gateway API actually has started off as an ingress API for traffic in the north-south direction, but now is also supporting east-west, service-to-service networking. And so the CDN project is also implementing services and multi-cluster services under as implementations of the Kubernetes Gateway API, in addition to the Kubernetes original Kubernetes APIs as well as the Cilium APIs, right? So this is how you can think about it. So a lot of these projects, they start off and then they add support for additional, the controller can service additional APIs. And I think this will continue to evolve. They look to be adding more service mesh type APIs, for which I think they will leverage the Kubernetes Gateway API mesh mode and continue to evolve along however the Kubernetes projects and the Cilium project evolves. I'll come back to this. There's some more subtle detail here, but hopefully you get the picture here, right? So keep in mind, in addition to all of this, the Kubernetes Service API, well, I don't expect that we'll have a V2 of this API, but there could be future extensions along, perhaps under the umbrella of the multi-cluster service API, right? There's also the network policy API, which again is currently single cluster. There have been proposals and discussions in the past to extend it to multi-cluster. That is still TBD, how that would evolve. If you look at the Istio APIs, though, they started off as with their own set of Istio native APIs, right? So they use the Kubernetes, group value kind of infrastructure and so on. But these were all Kubernetes. These were all CRDs. They were not really based on the Kubernetes APIs originally, right? And so they had these ingress gateway APIs as well as mesh east-west APIs from the beginning as multi-cluster, right? We saw in the earlier slide that the notion of a service in Istio is implicitly multi-cluster. That project also has now added controllers to implement the gateway API, initially for the gateway mode, and later on through the Gamma project, that same API, but in mesh mode, right? And there's also this ambient mode that is being added as sort of an optimization of the Istio project. So you can see that the Istio project is continuing to evolve. They will continue to support more and more the gateway API as another way of supporting multi-cluster features. And I think that although currently on the network policy side, they have their own auth it remains to be seen whether they, especially now with ambient mode, where there's an L4 auth whether some of that could align with the Kubernetes network policy or vice versa. And then finally, we talk about here the Kubernetes Gateway API, which has the scope of this API has become broader over the last couple of years. It started off as a V2, as a newer version of the Kubernetes Ingress API to address some of the limitations of the Ingress API. But then it, evolved into having different uh, resources for different operational personas. And then it was decided to add a mesh mode, which is what the Gamma project that you might have heard of sought to bring in. And there are some of these gaps which sort of brought these capabilities in. And these are all now in the GA version of, of the Kubernetes API, Gateway API. And then some amount of explicit multi-cluster support also came in through another of the gap. And this one in particular allowed you to use some of the multi-cluster services API objects like service exports and imports as backends for the gateway backends, right? So I think the Kubernetes Gateway API continues to evolve. It is sort of taking on both the ingress and the service mesh space. It will it will align more with other Kubernetes native APIs like the Kubernetes multi-cluster services API. Particular implementations of this could be doing more than others. So for example, we talked about how the Istio controller implements the gateway API. And I think we have to watch how this evolves. I think there's still going to be work to define versions of the gateway API that potentially could subsume the capabilities of some or all of the service mesh and the lower layer networking, but I think that's a while away. So I think all of these projects are going to be continuing to develop their APIs. You have to be aware of which functionality you can use through a common Kubernetes API like Gateway API, and for which you want to stick with the native project APIs. So I think this is an important area to understand and watch the upstream communities. Again, there's more here, but I think hopefully for now, this is an adequate summary. We talked about the Kubernetes gateway and mesh modes. Here's an example. So it's the same API, right? Gateway.networking v1. And it's an L7 route in both cases, but in one case, the route is attached to a gateway, right? So here you see that the parent ref is a side attached to something that has a label, but it actually is a gateway implementation. Gateway being another resource in the Kubernetes Gateway API suite. And it points to a backend, which is a service. In the mesh application, a very, very similar use of the same API, but now this time, instead of attaching it to a gateway as a parent, attaching it to another service, a service as a parent allows you to do service to service mesh networking with very similar L7 traffic management as the original gateway API. So this is sort of a way of thinking about how the gateway API uh, is sort of becoming a broader vehicle in the Kubernetes native API space. And I think you want to watch all of these different projects to see how they align with some or all of this gateway API, while continuing to likely have their own functionality for quite a while. I mean, I think that's the situation I see for the next few years. But it's good to be aware of the details of how these evolves, APIs and projects are evolving. And finally, again, I think a Cilium multi-cluster example, we mentioned earlier that in the case of the service API, Cilium just adds some annotations to extend it somewhat seamlessly to multi-cluster. And this example shows those three annotations. I'm not going to go into details on these, but essentially it controls whether a cluster thinks of a service as being accessible from another cluster as a global service, whether it wants to share its backend to the other clusters, and whether the load balancing should have local preference in terms of affinity or not. So using these simple annotations, it is fairly seamless to extend a unicluster service to multi-cluster. For Istio, on the other hand, as we said earlier, you don't not even need this, although it also has some features to do affinity-based load balancing. And then the multi-cluster network policy for Cilium is fairly comprehensive. So here's an example where you use the Cilium network policy, but it is very, very similar to a single cluster network policy. They have added some extra label matches for their endpoint selectors to be able to match on cluster name, for example, as shown here. But even if you don't use that, you can just do endpoint pod label matching. And it has a control plane that essentially synchronizes that information across all clusters in a cluster mesh. And so I think that's a nice way of sort of making it very seamless, both for multi-cluster service and multi-cluster policy. Okay. So let's move on to guidelines and recommendations. We talked about patterns, we talked about projects and APIs. My suggested recommendations would be that you do want to start, if you haven't already, with a design plan for multi-cluster Kubernetes. Sooner or later, you will need to do this, I believe. And so regardless of whether you implement it or not, it's good to plan for it. And think holistically, not just about networking, but all the other DevOps aspects we mentioned earlier, things like application deployment and lifecycle management, observability, and so on, right? Design and architecture along all of those lines. Definitely start simple, and you do not need to implement complex features right away, right? Hold the line. You can always say no initially. This is a nice quote by Solomon Hykes. No is temporary. You can always change that later. But once you say yes, you may introduce some complexity for which you may not have the best solution right now. So be careful, but think about it and definitely design for it, but implement in phases, right? Of course, if you do need to complex, there are many reasons you do need the full complexity of solution patterns we talked about earlier. Don't be shy. The tools exist. Using guidelines like what we're suggesting here and sort of a fairly deep analysis on your own, I think you'll be able to come up with the right sort of tooling, right combination of tooling to have even complex topologies be supportable. And definitely consider a multi-phase, multi-stage roadmap. And one example is on the next slide. So let's look at that. Actually, it's on the slide before, for one more slide after this, but let's look at sort of the rules of thumb again, just to be clear. So the rules of thumb would be prioritize your north-south. These are mine, right? You may have, your mileage may vary. I think these are reasonably applicable to many, many enterprises. Prioritize the north-south networking first, right? In many cases, you will find you may not even need east-west multi-cluster. And it actually saves you a fair amount of complexity to not have to deal with east-west multi-cluster. Many apps can work well just with north-south multi-cluster load balancing and with other design parameters such as properly replicating um, all the app microservices to each cluster, taking care of state through global databases and things like that. If you do need east-west multi-cluster, um, prioritize the single network mode, right? Definitely simpler, fewer issues, less complexity, better for stateful workloads. In fact, I don't think you can do stateful workloads in multi-network mode um, because you need, for IP addressability. Better for load balancing, visibility, and performance. This does, though, require larger IP-free address pools and better IP management. So maybe you want to address that by using VPC features in the public cloud. Maybe, for example, use VPCs that have global reach rather than per region or other such features. And seriously consider IPv6 to ensure that your network is flat. I think IPv6 has achieved a fair degree of maturity in the Kubernetes space and in these different projects that it is worthwhile trying to stick to a single network model and, if needed, leverage IPv6. So that's the second stage, right? Second recommendation. Yes, for truly advanced and large scale or geo-distributed deployments, you will need to and you should evaluate full multi-network, multi-mesh, federated global federated topologies, global anycast, and so on. So that's where you should educate yourself, and maybe your requirements are complex enough to get there at some point or the other. Of course, as we said earlier, evaluate the non-networking aspects at the same time. They can make a huge difference in terms of, app orchestration and visibility. And definitely align with your organizational and your operational model, right? What kind of lifecycle management tools you have, and are your teams ready? Are you able to delegate some of that to business units? What makes sense? What kinds of applications you expect to encounter? Can you create special cluster stub zones for those occasionally few complex applications and keep the rest of the network simple? Um, do all that. Prioritize simplicity. Um, you know, Follow this path. You can even consider user space options, as we said earlier. That's a very convenient model if you want to, if your infrastructure team has not provided an IT-driven service mesh, use the user space option in that case. Okay, so I decided to break this into 3 levels. Level one, a level one multi-cluster solution, multi-cluster networking solution would be minimizing your intercluster dependency by having only north-south networking, right? So just have north-south load balancing, use your namespace sameness, okay? No need to, if you need to add automation to ensure namespace sameness while retaining self-service capabilities, do that. I think it's worthwhile sticking with namespace sameness. There are a few cases where that is restrictive, but in the majority of the cases, I think it's worthwhile to stick with namespace sameness. Most of the projects we talked about require namespace sameness. There are a few projects, I didn't mention projects like ClusterLink, and even, of course, the user space networking projects that are not dependent upon namespace sameness. But I think at level one, stick with namespace sameness, stick with north-south. Level two, add some basic east-west networking, but try as much as possible to keep it to single network and flat network mode only, right? Uh, do your IP address management. If you cannot do it with IPv4, if you cannot do it with IPv6, I think all of these projects are very, very mature now with IPv6. It would be very worthwhile to have a single network model. You may need to have simple multi-mesh as well in the level two, and that's okay. But if you have these other restrictions, I think you'll be okay at level 2. And then if you've already done these, or your apps require additional, your enterprise requires additional functionality, then you can go to level 3. You can then look at multi-network mode, remote clusters. That's another pattern we didn't talk about. That's when your control plane is in one cluster and your data plane is in a different cluster. That's where you will need to address things like multi-organization, multiple roots of trust, and so on. And although we didn't cover that, some of these projects, in particular the service meshes, have a more complex, a more comprehensive support of multiple trust domains, and you should be evaluating that. Also, if you have to deal with higher scale, I think a lot of the things we talked about, most of the projects are, many of them might be similar when you're at small scale, but there's a significant number of issues to deal with when you want to get into the scale of hundreds, thousands, or even tens of thousands of clusters. You will need to, for example, the CDN project has this KV store mesh, which is another way of scaling their multi-cluster control plane. You will need to think about the global Anycast kinds of solutions from public clouds. So think about these 3 levels. Start from the top. And of course, if you're using a user space networking project like Scupper, actually, some of these terminologies don't quite apply, right? Scupper is implicitly agnostic to namespaces, for example, so the namespace criterion doesn't really apply. And it treats sort of north-south and east-west networking a bit more equivalently. So for those, again, some of these levels would apply, but again, the basic philosophy of starting with simple north-south load balancing and then moving on to level 3, I think is the good strategy. We'll do one demo here, which is a simple level 1 type solution. We talked about having in level 1 just north-south load balancing, and many use cases can be met just by doing that. You don't need to do any east-west load balancing at all. So let's think about what happens, but there might still be some gotchas which you need to think through. So let's say we are doing this solution here, and we've got this application complete, with 3 microservices. All microservices of that application are fully replicated in cluster 1 and cluster 2. And let's say we are using some project like KHGB to do the north-south load balancing through DNS global load balancing. Well, one of the gotchas is that the global load balancing controllers watch for the health of the services that the ingresses is routing to. But they may not be aware of the entire application's health, including services which are deeper in the service graph, right? So in this case, if the red microservice goes down, and if you're using a load balancer or multi-cluster load balancer like KGB, it will not be aware of this. And so it will continue to see that as long as the green service is up, it thinks that I can continue to, have clients coming to this cluster, and the backing service for the route is up. But you really don't want to do that. You want to maybe have the controller be aware of that, and that today is not handled. So we'll show a demo of how, with a simple, more complex health check and possibly some operators to implement that, you can address some of these gaps and make your simple level 1 north-south load balancer a more robust solution. Okay. Another point to mention there is that if we're doing that already, one can conceivably think of an operator which is completely programmable, right? It can say things like, I need at least 2 instances out of 3, or maybe I need more than 50% of my backend replicas of the green service to be up. I need at least 1 instance of the blue service. and I need at least X number of instances of the red service for this cluster to receive to adequately perform in and receive traffic. If not, even though I may have some backends of all of these services, I might still want to um, stop advertising this cluster as a destination to the clients. Note that the clients might still keep sending to this cluster. So this is because of the DNS caching issues I mentioned earlier. But this allows you to detect a degrading application upfront and start offsetting and moving some traffic to the other clusters in advance of full catastrophic failure. So this feature that we're talking about in this demo can be used quite generically. And right now I did a quite a short operator to implement this for the demo, but I think I'm considering making this a proper operator for Kubernetes. So let's actually, I have a recorded demo, so let's just watch the recording and I'll just talk you through it. So here I've got on the bottom left, we'll see that we've got 3 clusters. We've got 2 GSLB 1 and 2, the actual application workload clusters, and HDNS representing the DNS service. If you look at the application, it has 3 microservices, front end, tier 2, and tier 3. That's in cluster 1. Let's look at cluster 2. Again, front end, tier 2, and tier 3. So as we said earlier, let's actually pause this for a second here. So so we've got one replica of the front-end port, and it's available on both clusters, and 3 replicas each of the tier 2 and the tier 3 microservices. And I've got a controller running, which requires at least one port of, sorry, I think it's got at least one port of the tier 2 and one of the tier 3 to be running, right? If if one of the 3 fails, that's okay. But if 2 out of the 3 fails, then before the third fail, we want to trigger the global load balancer to route away, right? So let's see that happening. So on the top, we've got an application. Actually, this is the demo application from the KGB repo, where there's an application sending to 2 clusters. Cluster 1 is in EU, and cluster 2 is in the US. And the load balancer has been set up in primary standby mode. So by default, all traffic for this application goes to the EU cluster. So you can see that at the moment, both applications and both clusters are healthy. All the traffic is being sent to the EU cluster. That's how the DNS resolution has been set up for this particular client. Now, what we're going to do is we're going to scale the application down, right? And we're making the front end down, application replica 0, and we see that the load balancer has now switched to the US. So if the application immediately backing the route is down, then yes, of course, like a regular load balancer, we want to route away. And when we restore that the initial backend service, we see that the traffic is restored to the EU cluster. This is fine. This is how the load balancer works today. But as we said earlier, when other services go down, normally that wouldn't be detected. But because we've got this operator running here, first, let's see, when we scale that tier 2 service down to 2 replicas instead of 3, the operator decides, okay, that is still acceptable. And it continues to prefer traffic to come into cluster 1. Same thing, even if the tier 3 application is brought down from 3 replicas to 2, it's still coming to EU cluster, right? So the operator decides that that is still okay. Now let's see what we're going to do here. We're going to, okay, so we confirm that we've now got 2 instead of 3 instances in cluster 1, but the operator decides that is still okay. Now what we're going to do is we're going to check the tier 2 microservice and change it to have 1 replica, right? So we did that, and you see on the top, it has now switched to US. So the operator decided that, okay, although all the services are up, but there is some service deeper down the service graph, which is not healthy enough. And I'm going to proactively start moving traffic to the other cluster. And so now all the traffic is going to the US. And of course, in the last thing we did there was we again restored it to 2 replicas, and the operator said, okay, you know what, this application is healthy again, and we are back to EU. So essentially you saw that we do need some additional automation. This is something that I realized that none of the current health check operators do this kind of function, and I think there's a need for this. So I just kind of did a quick demo for this talk, but I can kind of make it more formal. But this allowed you to make the simple level 1 north-south multi-cluster more robust. So you do want to think about all of these aspects, whether you're doing the multi-cluster at level 1 or level 2 or even level 3. We're just sort of looking at the other aspects of the GSLB here, things like setting the DNS TTL and so on. So anyway, that was sort of the quickie demo. And what that showed us was that you can make north-south go a long way, but there are still some gaps. And I think using automation like the one that I just demoed, you can make your solution more robust without needing to make it more complex. Although in some cases, you do need the complexity. So we conclude by saying that plan your multi-cluster roadmap in a phased manner. Definitely start with level 1, maybe level 2. Go ahead and plan for level 3 if you need to, but implement it conservatively. We talked about the many projects in the space, and we showed some analysis to see how these meet many of the patterns that we talked about. I would definitely recommend understanding the low-level data plane and control plane operation details, because they do affect functionality and performance. Feel free to reach out to me. I have played with many of these projects in hands-on and in a fair amount of details, so I'm happy to share my thoughts and findings. And so one of the questions was, are we there yet for multi-cluster Kubernetes? And I would say yes, although it's a journey, and I think there's more to come. So I think we've got a lot of the pieces, but you do need that good analysis, and you do need a proper phased strategy for having a successful multi-cluster Kubernetes deployment. This is some of my contact information, and feel free to contact me. Thank you.